All right, if there are no other questions right now, I will stop sharing. And I would say we move on to our first scientific talk of the meeting, which will be given by Arushi Saxena. Arushi, if you want to, feel free to share your screen. And the talk will be about high-resolution mantle flow models. Feel free to take it away.
Yeah, thank you. Thank you for the opportunity. So I will be talking about the mantle flow models, and these are the models which reveal importance of plate boundary geometry and slab pull forces on plate motions. This is the work I did with Juliana Danberg, Rani Kessmuller, Menno Freitas, Timo Heister, and Richard Styrel. As we are all aware, complex life on Earth would not exist without plate tectonics. And if we look at the earthquake epicenter distribution, which is here shown by gray circles, and volcanic distribution, which is shown here by red triangles, they lie very closely on plate boundaries, which means that if we can understand the plate boundary driving forces, we can also understand the hazard associated with these earthquakes and volcanoes. And just for this reason, there are several existing models. And these are some of the models in last 15 years. And if you look at the modeled velocities and compare it with the observed GPS velocities, they do a reasonable job of fitting the modeled velocities with the observations. So you may want to ask why we want to do this. And the reason is that these models, they all come at different conclusions with respect to what are the driving forces. So for example, Stadler in 2010, they proposed that slab pull until mantle transition zone is the main driving force, while Anthony Tutu in 2018, they proposed that most of the driving force comes from the lower mantle, and differences exist in these two studies as well. So one thing we want to do is resolve this discrepancy as to what are the main driving forces for these observed plate motions. And another thing you would notice is that if like the plate boundary geometries in all of these models, it's very simplified. It comes from a model which is Nivelle model, and it came out in 1990, so over 25 years ago. And since then, we have not really used complicated plate boundary geometry models, even though they exist, and we have not quantified the effect of the different plate boundary models on the observed surface velocities. So in order to address that, we use additional plate boundary models besides the Nivelle model, which is the simplified model here. And one model we use is the Peter Bird's model, which came out in 2003. And this includes additional microplates on top of the Nivelle model. But both of these models they come from GPS studies, and they are closed polygons. So they form closed polygons, and they don't have dip information. So these are the vertical plate boundaries. But in 2018, another model came up, which is the global earthquake model, and I will refer it to GEM model from here on. So this model does not have closed plate boundaries, as you can see in the Nivelle and Bird closed plate boundary model. Additionally, it also has these diffuse zones, which are these crustal deformation zones that extend in the continental regions. So like one thing we can already physically distinguish between these models is the importance of dipping and vertical plate boundaries, and also the difference between open and closed plate boundary geometry. The Bird GEM model is another model which we developed from GEM model, and this model does not include these diffuse deformation zones or these diffuse crustal zones. So using these plate boundary geometry models, we can quantify what's the effect on the surface plate motions. And we do that using a global tomography data. So we base our models' physical properties from global tomography data. In particular, we use a model which came out in 2016, and it's based on both P and S wave anomalies. So this shows some isosurfaces at -1 and -1%. So red are the hotter regions or the low velocities. And I already said hotter because once we convert it to equivalent temperatures using a constant scaling, we can see these low velocity anomalies to be higher temperature regions. And we use a depth-dependent scaling factor from Steinberger and Calderwood in 2006. And we only do that below a certain depth, specifically 200 kilometers. And the reason for that is that tomography near the surface is very diffuse, so it does not really represent the lithospheric structure well. So near the surface, we use another temperature model, which is the TM1 model. And this model includes the cooling of oceanic lithosphere and different ages of continental regions. So using these temperatures, we compute our buoyancy in our model using depth-dependent thermal expansivity. And that determines the buoyancy field or the driving forces. How our material deforms is purely viscous. So our models are purely viscous, and it uses composite creep rheology. And because the viscosity derives from temperatures, we have lateral variations in viscosities, but these lateral variations in viscosity are they're too large. So we scale them to a one-dimensional viscosity profile, which comes from geoid inversion. So this is the one-dimensional viscosity profile on which these lateral viscosity variations are scaled. And because we want to facilitate plate-like deformation, we additionally prescribe narrow regions of weak zones or low viscosities, and we do that using World Builder to get the complicated plate boundary geometry. So here is where we prescribe the different plate boundary models. And we set up our models in aspect and use adaptive mesh refinement so that the smallest cell size is 15 kilometers, and our models are compressible, instantaneous, with prescribed temperature. So we do not solve for the temperature equation, but they are compressible. And because we want to understand the influence of different forces, what we look at in the parameter study is how does the frictional forces along these plate boundaries change? So what is the effect of plate boundary viscosity on the surface motions? And how does the friction forces at the base of lithosphere change? So that is the effect of modifying viscosity of asthenosphere. And what is the plate boundary geometry effect on the observation? So that is the chosen plate boundary geometry model in our case. So in order to quantify our results, we use the GPS data from a no-net rotation frame, and we compute the residual with respect to the observed GPS. So here the blue vector shows the observed GPS velocity, and the black is the modeled velocity. So we compute three different kind of fits. One is the directional fit that just measures how different our modeled velocity vector is from the observation. Another is the speed residual, which only measures the magnitude misfit with respect to the observation. And the third one is velocity residual, which includes both direction and magnitude in the observations. So first, we fix the plate boundary geometry model and only look at the effect of varying plate boundary viscosity and asthenosphere viscosity. So this plot shows increasing plate boundary viscosity from left to right, and then the vertically increasing asthenosphere viscosity from bottom to top. And each model, each of these, like these globes are the velocity residual with respect to the GPS, and redder colors are the models that are too fast with respect to the GPS values, and blue colors are the models that are too slow with respect to the GPS velocities. The whiter models are the models that fit well with the GPS velocities. And what you would expect already is that if we reduce the asthenosphere viscosity and plate boundary viscosity too much, the models become too fast. And on the other hand, if we increase the frictional forces a lot, the models become too slow. But then there is a sweet spot with intermediate plate boundary viscosity and low asthenosphere viscosity, where we get a good fit with respect to the GPS values. So here we did not change the plate boundary velocity model, but only looked at the effect of the friction along the plate boundaries and at the base of the lithospheric plates. So in the next case, what we do is we choose some values of viscosity, plate boundary viscosity and asthenosphere viscosity near this good fit region, and do this like quantify our misfit for different plate boundary geometry models. So this plot shows in each column the different plate boundary geometry models that we looked at. And the x-axis is increasing plate boundary viscosity, and the y-axis is increasing asthenosphere viscosity. And the rows represent different misfits. So the first row is angular correlation or the directional misfit. The second row is the misfit only in speeds. And the last row includes both direction and magnitude of misfit. The lighter color circles are the circles that fit well with the GPS values in each of these subplots. So one thing what you can already see is that the directional fit improves if we increase the fault viscosity. So you can see that as you go from left to right, we have lighter colors or good fit with respect to the direction. And another thing which I want to point out here is that if we look at the velocity residual case only, like because it includes both angular fit and the speed residual, the maximum misfit is observed for the Nouvelle model. It's 2.52 centimeters per year. And the least residual is actually observed for the GEM model, which is the most complicated model in our parameter study. So what we want to do next is investigate which regions fit well. So we look at the spatial distribution of our best fit model for each plate boundary geometry. So these are the plotted velocity residuals for each best fitting plate boundary geometry model. And lighter regions are the regions that fit well with respect to the observations, and darker regions are the regions that do not fit well with the observations. So Nouvelle, as we looked at, has the maximum misfit, but it fits very well the Pacific plate, and everywhere else it has a high misfit. On the other hand, the GEM model, which has the best fit with respect to the observation, it has slower, we model slower velocities in the Pacific and Nazca plates or the fast moving plates, but everywhere else the fit is good. And the overall fit is best for the GEM model, which we can also see in these bar charts here. So the lighter colors are the good fitting model, which is the GEM model in our case. And just to put some numbers, we get about 93% of angular fit for GEM model and 2.05 centimeters per year misfit with respect to the observations. And what this study already shows us is that because GEM model fits best, what we can think of is that in reality, plate boundaries are not uniformly weak. And because GEM model has dipping plate boundaries, it means that if we have dipping plate boundaries, the slabs, which are also dipping, can transfer the slab pull more effectively. So we also compare our best fitting GEM model strain rates with respect to the observed strain rates. So on the right is the global strain rate model, and on the left is our best fitting model with the strain rates in our best fitting model. And we can identify 3 zones. Number 1 is the zones of very high deformation, which is the red color here, which also matches these discrete zones of very high deformation in the observations. And then we also find an intermediate strain rate zones, which is these diffuse crustal regions. So these are the faults that only extend until crustal depths, but they can already localize deformation here due to variable with lithospheric structure and rheology that we have. And these also match what is the diffuse zones in the observations. And then third zone is very low deformation. And this is the blue region here. And because the observations did not have any data here, it's just white because there's no strain rate value here. It's very, very low. So what we want to say here is that our models match the strain rates with the observed strain rates pretty well. So next, because we also want to look at the influence of upper mantle versus lower mantle, what we do is that we isolate the effect of just the upper mantle, and that is the TM1 only model. And what this shows is that the fraction of the model speed with respect to the model which has both upper mantle and lower mantle. And the pink or the hotter colors are the regions that fit, that have high velocities. And bluer colors are the regions that have low velocities. But what I want to stress here is that just with the heterogeneity in the upper mantle, we have about 73% of the modeled velocity compared to 100%, which has both upper mantle and lower mantle. So what we can think of it as physically is that slab pull in the upper mantle alone can explain 3/4 of the observed velocities. And by including the heterogeneity only in lower mantle, we can explain only 1/4 of the observed velocities. So in summary, we looked at the influence of plate boundary geometry, and we find that the GEM model has the best fit, and it diffuse deformation zones. They are more realistic in explaining how the plate boundaries look like in reality. And what is the balance between the tectonic forces? We find that slab pull in the upper mantle is the most important driving force. And right now, because we realize the importance of slab pull, we are trying to incorporate more realistic slabs using slab 2 models. So this is just a plot which shows the slabs on the globe, and the colors represent the depth of the slab. And this is a cross section for the slabs and the temperatures showing the slab. So next, we want to improve our slab structures and look at different geologies. Thank you.
Great. Thank you so much. If there is one very short question, we may be able to put this in right now. Otherwise, we will have time for questions later.
I have a question. Hi, Arushi.
Hi,
I was
Singo.
surprised you explore many models using the global model. So I was wondering how many did you have? How many cores did you take for your model, and how long did it take running time for most expensive problem?
Yeah, I forgot to mention that, but I use close to 5,300 cores, and these models.
Wow.
Yeah, and this takes 3 hours compute time.
Just instantaneous, right?
Instantaneous, yeah.
Okay, thank you.
Thank you. Yeah.
Great, thank you. So if you have questions, please note them, keep them for later. And we will move on to our second talk in this first session, which is given by Becky. If you want to share your screen, go ahead. And we will talk a bit more about slabs and their internal dynamics, I think. Feel free to take it away. At the moment, you're muted.
Yeah, sorry, I was just moving my windows around.
Okay, perfect.
Okay, you should be able to see my slides now.
Yes, we see the slide
Okay.
and we hear you.
Perfect. Okay. Yeah, so I'm Becky and I'm working with Magali Billen at UC Davis. And this is my presentation from AGU, but with more of the modeling side added in, but left in some of the context of why I'm setting up these subduction models. But yeah, kind of a theme here of strain rates and some Slab 2.0 data that I'll talk about as well. So like I said, I'm interested in tying deep earthquake conditions with subduction models. So just for context of where I'm thinking about these things, deep earthquakes are occurring in subducting slabs from about 70 kilometers down to 660 kilometers. And how they occur is still kind of an ongoing question. So there's 3 proposed failure mechanisms that could all be active in the slab, acting together independently. But broadly thinking about the conditions that they occur under, is previously proposed that you need low temperature and high stress. But each of these failure mechanisms also depend on strain rate as an important condition for the failure mechanisms to occur. And so let me just hide that. Okay. In 2020, Magali had this paper that proposed that strain rate was another general constraint on where deep earthquakes occur. So she did some subduction modeling, which you can see a snapshot of here on the left, and calculated strain rates. And so this panel B here is showing strain rate depth profiles. You can see there's depths where we have higher strain rates, lower strain rates, and then higher strain rates again. And what she did was she compared these models with similarly shaped subduction zones and compared where deep earthquakes were occurring and found this correlation between depths where we had deep earthquakes and we were calculating higher strain rates, gaps in seismicity, and decreases in strain rate. And so this led to the proposal that strain rate is another constraint on where deep earthquakes occur, and in particular that high strain rate depths correlate with deep earthquakes. So what I'm doing is a retesting of this strain rate hypothesis by making some updated models, subduction models in Aspect to address some of the limitations of her models from the 2020 paper. So those models did not include, they were just they were viscous and had yielding, but did not include low temperature plasticity or elasticity, which are both very important for calculating the strain rates and stresses in the slab. The models themselves were also not built for a specific location. They were compared with similarly shaped slabs. And so having both elasticity and being able to build a location-specific model are important for when we're trying to compare with deep earthquake observations, both in terms of the locations of the earthquakes and the stress orientations that we see in the slab and we observe. So one of the things I'll talk about is this challenge of keeping a present day geometry for a specific location, but building up elastic stresses in the slab. And then lastly, the study did not differentiate between those three failure mechanisms that I mentioned of how deep earthquakes could be occurring. So at the end, I'll kind of zoom out and talk big picture about how we can use these subduction modeling results as a lens to guide deep earthquake failure mechanism. So our updated subduction model is done in aspect. The model domain shown over here on the right, a 2D chunk model extending from Earth's surface down to the core mantle boundary. I have free slip conditions on the top and bottom and open side boundaries. And it includes viscoelastic plastic rheology, like I said, incorporating especially that low temperature plasticity and elasticity that we did not have in the previous models. I have a non-uniform mesh. So our highest refinement is in the slab and lithosphere where we're interested in those conditions, using the isosurfaces strategy to refine based on a temperature contour, and then kind of coarsen as a function of depth using the minimum and maximum refinement function. So we really have our finest resolution of a 1.5 kilometers about in the slab, and then coarsen outwards from there and with depth. Zooming in on the slab itself, a 2-layer slab with a crust and Hartsbergite layer, and then the pyrrolite mantle. And also incorporating the olivine and pyroxene phase transitions, which you can see over here on the right in the density field as well. And those are incorporated for each compositional layer and for the background mantle as well. So this is kind of the general setup, but like I said, we want the slab to represent a real location on Earth because we're going to be comparing with real observed earthquakes. And so how we can do that is take this general model setup, but then set up a model for a specific location on Earth using observations. So I do this in World Builder, working with Menno. And for the geometry of the slab, we can use these, the Slab 2.0 data shown over here on the left, which the color field is showing extending from trenches depth to slab. And we have that from seismic data. And then we can use observed plate ages and velocities to inform our thermal structure. So I use a half-space cooling model for the plates at the surface, and then a newer mass conserving temperature model that Magley has been implementing in World Builder for the slab. And so in this way, we can take our general model setup with the rheology and phase transitions that we want, and then tailor it to a specific location that we want to look at for their deep earthquake activity. So I'm going to walk you through an example of this workflow of setting up one of these models, show you a short run of one, and then some of the preliminary results. So I'm going to zoom in here on the Tonga Kermadec Trench. And what you're seeing here in the light blue is the trench itself, and then extending from it is that color field of showing depth to slab. And then the dark blue lines to just a simplified plate construction at the surface. So I choose a trench perpendicular profile extending away from the Kermadec Trench. And you can see that the Slab 2.0 data in this region only goes down to just below 600 kilometers here. So I'm going to be supplementing the Slab 2.0 seismic data with some regional tomography to infer what that deeper slab geometry is. So we can take this seismic data and construct the geometry of a cross section. And so we have this cross section going from A to A prime, cutting through the Kermadec Trench here, and use that to set up our geometry over here, where we have subduction, we have spreading, and then we have our slab geometry, like I said, from a combination of that slab 2.0 data and inferred from the tomography. And then bringing in observed plate ages and velocities to set up the temperature model, which is what you're looking at in this model domain here. So this is all done in World Builder, and then bring that into Aspect and run that. I'm just going to zoom in here because, as I said, we're focused on the deep earthquakes and the slab conditions itself. So all of the results and like model runs I'm going to show are just going to be focused on this part of the model domain. Okay. So as I said, running the model, we have this challenge of wanting to keep that present day geometry that we just built, but also build up elastic stresses. And so the way that we're doing that is we have advection on, but we hold all the compositional fields static except for the stresses. So the stresses are tracked as compositional fields. And so we allow these to advect, but hold all the other compositions static. And then additionally, we hold the temperature field as static. And this was an option that I implemented a few hackathons ago to function just the same as the compositional fields when they're held static. So again, everything is held static except for the elastic stresses that are allowed to advect and build up. And so I'll show you what that looks like. What you're going to see over on the left is the color field is the magnitude of the stress that's going to run over a short amount of time. And the slab geometry I'm representing here by just showing in white the 1600 Kelvin contour for reference. So you can see what the general slab geometry shape is. And then over on the right-hand side, you're going to see it's going to track the stress buildup for this location that I just picked deep within the slab. And so as it's running, you see the stresses building up. We have this initial elastic response in the beginning, and then kind of moving into this viscous regime here. And so we have this nice viscoelastic curve for this point down deep in the slab. So we only are going to run these for a very short amount of time and just want to build it up to get those stress levels in the slab. So once we do that, we get our solution fields, and going back to that main idea of first retesting the strain rate hypothesis. What you're looking at here on the left is the strain rate, and I just have it kind of mapped within the cold core of the slab where we would be expecting deep earthquakes. And then what I have on the right for comparison is the earthquakes for the Kermadec region, so for where this particular profile that I made came from. And so as kind of a first just retesting of comparison with models and observations, we can see we have depths where we have higher strain rates in the more yellows and greens correlating with higher earthquake activity. We have lower strain rates correlating with depths where we see a decrease in earthquake activity. And then we see increases in high strain rates at these deeper depths again, correlating with an increase in seismicity. And so this is good agreement between our modeled strain rates and our seismic strain rates, our observed earthquake activity. Now, since we also included elasticity, as I mentioned, we can evaluate our models by looking at the stress orientations. And so plotted on top of the strain rate solution here are the unscaled principal compression orientations, and they're colored by stress magnitude. And another good thing that we saw in these models were that in the cold core of the slab, we see this down dip compression region, which with Slabs' geometry is something we see in the deep earthquake observations from their focal mechanism solutions. So since this is a particular profile within the subduction zone, we can pull the earthquakes for that particular profile as another check on our model and compare the computed p-axis orientations that were the same from the previous slide with the computed p-axis orientations from the focal mechanism solutions of the actual earthquakes and compare between our model and our earthquake observations. And so a couple just first glance checks is we do see some good agreement between where we have some down dip compression on the front side of the slab and then some more horizontal orientations in the back, some more complicated changes in down dip compression orientations as we go deeper down. But this is kind of the sort of comparison we'll do and more thoroughly for multiple profiles within this subduction zone, as well as also investigating some other subduction zones with different earthquake activity, ages, velocities, different characteristics for a more thorough investigation. And then kind of lastly, I said we'd zoom out. So after that retesting of the strain rate hypothesis and evaluating our models, we can use the results from our subduction modeling to kind of direct our investigation of how these deep earthquakes are occurring. So assuming moving forward, the strain rate hypothesis holds with the retest, we would expect that deep earthquakes are occurring in regions in the slab here where we have high strain rates, high stresses, and low temperatures. And we can take the conditions that we model from the slab and use those as initial conditions in a separate model that would test one of those failure mechanisms. So use this as kind of a lens to guide what conditions we're testing in a separate model for a failure mechanism. And in particular, I'm interested in thermal shear instability. And so using these two separate models to investigate this particular mechanism, but driven by the subduction modeling results. So in summary, I'm updating the subduction models and I'm using the world builder and aspect to set up the numerical models and first retest that strain rate hypothesis, looking at the conditions in the slab, and then evaluating that with the seismological observations, and then ultimately use those as results to investigate thermal shear instability as one of these potential mechanisms for deep earthquakes.
Exciting. Thank you. We have maybe time for one question, and otherwise we'll postpone everything else to later.
I have a question.
If you want to, yeah. Go ahead, Gary.
Yeah, sure, Becky. You said mass conserving, the temperature algorithm was mass conserving. Did you mean it was energy conserving? The temperature, the energy is conserved? When you said mass conserving temperature algorithm, I was a little confused.
Yeah. Yeah, Magley could probably answer this better.
It's the same. It turns out because the mass is temperature dependent, right? It's varying with the density varies with temperature. So when you write down the equations, you can think of it as either conserving mass or conserving energy. But since people usually think about the mass of the slab as being related to the force and what's actually causing deformation, I found that it just makes more sense to people to call it mass conserving.
Got it. Thank you.
Awesome. Then thanks again to both of our first speakers for a very interesting first session.